Welcome to this introduction for our paper, Size Types with Usage for Parallel Complexity of Pi Calculus Processes. In this paper, we aim at designing a type system to analyze the parallel complexity of Pi Calculus processes. Let me introduce some keywords of this title. So Pi Calculus is just a language for parallel computation when you have parallelism, communication with channels, and when we can send values and name of other channels. This Pi Calculus, we study parallel complexity. So the span, complexity under maximal parallelism. The intuition is that we can do a bunch of computation, independent computation in parallel. For this, we will use 4 size types, where the idea is to track the values of, for example, integer in the processes, which is very useful for pattern matching and recursion. And we will use usage. And the idea is that we look at the behavior of channels independently from the others. And for example, you have this that says that the channel uses an input that will be ready to receive a message from time t0 to time t0 plus tc, and then it continues. And with all that, we can design effectively a type system to analyze parallel complexity by calculus. Thank you.
Hello, I'm Felix Stutz from Max Planck Institute for Software Systems, and in our talk I will discuss how to verify asynchronous communication. For instance, if we are given such a simple load balancing protocol, it is fairly easy to come up with a candidate implementation for it. In contrast, to verify that this candidate implementation indeed implements the protocol in an asynchronous setting can be quite cumbersome. This is why our goal is to be correct by construction. We achieve this by borrowing ideas from the domain of multi-party session types. And we obtain an efficient algorithm which, given a global protocol specification, yields local specifications that are correct by construction. Previous MST frameworks employ severe restrictions on protocols in order to ensure correctness. Therefore, they cannot verify a lot of patterns from distributed computing. We waive some of these restrictions and, for example, allow a participant to send to different receivers when branching, and also to receive from different senders. In addition, we can rely on global information rather than only local information in our soundness arguments. Each of these features is even needed for this simple load balancing protocol from the beginning. In our talk, I will discuss in detail how we achieved to support these features and hence made the efficient MST verification techniques applicable to patterns from distributed computing.
Hi, this is Simon Fowler from the University of Glasgow. Our paper is about tightening the correspondence between linear logic and session-typed functional languages. The Curry-Howard correspondence tells us that propositions in logic can be thought of as types in the simply typed lambda calculus, proofs can be thought of as programs, and proof normalization can be thought of as evaluation. In 2010, Kairos and Fenning extended this correspondence to concurrent programming by demonstrating a logical basis for a process calculus with session types, which type communication protocols. This paper concentrates on GV, a session-typed linear functional language, and CP, a session-typed process calculus with strong ties to linear logic. Phil Wadler introduced both calculi in 2012, and Lindy and Morris later showed semantics-preserving translations in both directions. Unfortunately, GV has two issues. The first is that structural congruence does not preserve typing, which causes headaches when reasoning about the meta theory. The second is that the correspondence with CP is muddied by needing to use weak explicit substitutions. Inspired by hypersequent calculi and previous work on hypersequent CP, we moved to typing processes using multiple typing environments. As a result, we get a much nicer calculus with much stronger and more general results. Please come along to the talk to find out more.